Okay. Hi everyone. So I'm Marc Arène. So I'd like to thank the organizers for giving me the opportunity to talk today. So I'm a third-year PhD student here at APC, working under the supervision of Edward Porter, and I work in the gravitational wave field. So firstly, this talk is not about how we can use deep learning to replace some kind of MCMC sampler, but really how you can use deep learning to enhance your existing sampler, in that case, the Hamiltonian Monte Carlo sampler. So firstly, I'll quickly review how we do parameter estimation gravitational waves. Then I'll go on to the Hamiltonian Monte Carlo, so the HMC. Thanks to Tom this morning, you had an introduction on how it works, so hopefully I could go a bit fast on this. We'll see that there's a main bottleneck in the HMC, and in the third part, we'll see how we can circumvent this to build a competitive HMC. And it's only in the last part that I'll introduce how you can use DNNs to speed up your Hamiltonian Monte Carlo. Okay. So in gravitational wave data analysis, we model the signal that we observe with our ground-based detectors as the sum of a noise process that we think of Gaussian and stationary, together with a potential gravitational wave signal that depends on a set of astrophysical parameters. So in the simplest model, you have 9 parameters, such as distance or total mass. In the most complex model, you have 17 of them, and in my presentation, I'll restrict to 10 of them. So now we use, in the analysis, we use match filtering to dig out the signal that's buried in noise. Match filtering is known to be the optimal linear filter to do this. And as you can see on the video, it uses phase matching of the yellow template that we generate to dig out the potential signal in our data. All right, so we use Bayes' theorem to construct the posterior probability of our set of astrophysical parameters. And we use that formula for the likelihood, our likelihood. So you can see that we need to generate the yellow template for each likelihood evaluation, and we do a coherent network analysis by summing over the Hanford, Livingston, and Virgo detectors. So each time you want to calculate the likelihood, you have to generate a template and then cross-correlate it with do the weighted inner product with your blue signal, your blue data. So currently, parameter estimation analysis is carried out using parallel tempered MCMC and or nested sampling. So both of them, and it's quite important, are random walk samplers. Duration of the analysis can range from a few days to a few weeks, depending on the source that you're dealing with. For BBH, binary black hole, it's going to be a few days, and binary neutron star is going to be a few weeks. And that was the case for GW 170817, which is the famous first binary neutron star that was detected back in 2017. And that's actually the signal that I'm going to mention, that I run my analysis on, and for the presentation as well. For MCMC, the likelihood is evaluated about 10 to the 7 times, and then we get an effective sample size of about 10,000 uncorrelated samples. So about the HMC now, so very importantly, it's a non-random walk sampler, as Tom stressed this morning. So we're going to use Hamiltonian dynamics to propose the next sample, and it's been shown to be both theoretically and empirically d times more efficient than the random walk that you would do with MCMC. And D is the dimensionality of your parameter space, so 10 in my case. So here as it goes, you build your Hamiltonian with a potential energy that you construct by inverting your log posterior. So you really treat the problem as a sort of gravitational problem. And then for the kinetic energy, you introduce fictitious momenta together with a wisely chosen mass matrix that I'm not going to go into details. And then to make the link with Bayesian inference, we highlight that this Hamiltonian has a canonical distribution over phase space. As you can see, it is separable and variable, and so you can see here that the canonical distribution is directly proportional to to the posterior distribution. So that's really how you can sample from the posterior distribution. So to go from one, like the first red sample to the next one, what you need to do is really to solve Hamilton's equation and then stop the trajectory at some point, and that's how you get the next sample. This setup allows for really distant state space proposals, and since the probability to accept the next sample depends on the conservation of the Hamiltonian, and it should be conserved, the HMC produces a very high acceptance rate. So those two features are the main strength of the HMC, because you have a really small autocorrelation length. However, the cost for this is to compute the gradient of the log likelihood at each step in your trajectory. In gravitational wave astrophysics, unfortunately, we don't have any closed form solution. So we have to use numerical differencing. And so if you do central differencing for this, it means you have to compute 2 likelihoods for each of the 10 gradients at each step of the trajectory. And that's really costly. So here's the example of a Hamiltonian trajectory in d dimensions, projected, of course, here in 2 dimensions. So you start at somewhere. Oh, and the frames here are really the 68% credible interval of the end distribution. So that's for you to see that a single trajectory is able to travel a fair amount of distance of the posterior. So you run your trajectory by solving the Hamilton's equation. Then after here 200 steps, you're going to decide to stop the trajectory. That's then your proposal, then you draw new momenta, and you keep going on like this. So what you have to realize is just to get this sample, I had to compute 200, the number of steps, times 10, the number of parameters. So 2,000 numerical gradients. That means if I use central differencing, 4,000 waveforms to generate. And for 170817, one waveform generation is at least 15 milliseconds. So it means one numerical trajectory is going to be about a minute. So it's really long time just like to propose a new sample. So that's the main bottleneck of the HMC. So as a summary, advantage is the very small autocorrelation lengths. However, the price to pay is computation of numerical gradients. So the solution for this that we found, that we tried and is working, is to replace the numerical gradients with an analytical fit that's going to be much faster. And that's how you can build then a competitive HMC. So how do we do this? The idea is to replace the numerical gradients with a cubic fit, for which you have the formula here for each gradient. So you have some coefficients A to derive. The symmetry in d dimension means that for each gradient you have 286 coefficients, so 10 times 286 coefficients to derive. And so how do you derive them then? Well, the idea is to split the algorithm into 3 distinct phases. So in the first phase, we're going to run several hundred trajectories, numerical trajectories, and at each point of them, we're going to record the position and the values of the 10 gradients. Then in a second phase, we're going to derive with all this data that we've gathered 10 times 286 coefficients. And in phase 3, we just replace the gradients with our approximation. And this approximation is 1,300 times faster than the numerical gradients. So that's how we circumvent the bottleneck. So to make the link here with deep learning, even though I haven't talked about it, but what we're doing basically is we're building our training set, then fitting our model, and then running our fit, even though there's no deep learning here yet. But so now how well does the cubic fit do? So here you can see the regression plots for the cubic fit over a validation set that represent 10% of my training data that I've gathered during my first phase of the algorithm. So on the x-axis are the true values of the gradients, and on the y-axis are the cubic predictions for them. So we're doing really good for 7 parameters out of 10. So it's really nice. However, for 3 of them, it's really the cubic fit can't handle the distribution. The reason for this is actually that psi on the bottom left corner is multimodal, and then the 2 other parameters being highly correlated with psi they get screwed as well. The solution for this, without going into details, is that we're using ordered lookup tables that we built during phase 2. They allow for local fits, that's accurate, but then the price is that it's 10 times slower than the cubic fit. That's the end result, the result of a full HMC run on 170817. So in phase 3, we have 43% acceptance rate. One HMC trajectory is then 0.2 seconds. And so we have to wait 4.5 seconds to collect each new statistically independent sample. And so in the end, the whole run took 1 day. That's to compared with about 4 weeks that the current algorithms are taking. So that's our competitive HMC. And so it's always already quite a nice improvement, because we've built something that's like 30 times faster than the current parallel tempered MCMC. But can we use GNNs to speed it up even more? So as you might have guessed, the idea would be to replace the cubic fit by a neural network. So my network is the following. I have an input layer of dimension 10, obviously, then 3 internal layers of dimension with like 100 nodes, 1,000 nodes, and 100 nodes, and then an output layer which should produce the 10 gradients at the same time. I use Keras sequential model with the ReLU at each layer and the Adam optimizer. I'd like to highlight that it's really absolutely necessary for me to rescale all my data, because they have very different dynamic scales, and otherwise nothing would work. And for the training, I use 100 epochs and a batch size which represent about 1% of the training set. This is the training history, where the nice agreement between the two curves, I think, indicate there's no overfitting of my model, and the training takes 6 minutes, which is completely acceptable. So, as a reminder, that was how well or bad the cubic fit is doing. And to compare that with the neural network, you see that we do a lot better on the 3 troublesome parameters that we had before. And we do as good for the other ones. So now when we plug that instead of the cubic fit, so that was the results for my cubic fit, 2 minutes for the training, 43%, etc. So 6 minutes training, but now I have an acceptance rate which has gone from 43 to 52%. The time per trajectory is about the same, but since my acceptance rate is gone up, I collect statistically independent samples quicker. And so in the end, I gain like an hour on the entire phase 3. That was running the GNN with also the 3 other lookup tables. That's in order to like make an apples to apples comparison with the cubic fit. But since I'm doing better on the 3 troublesome parameters, I can just run the neural network alone. So these are preliminary results, so they're to be confirmed. But I'm highly confident that I should have a 45% acceptance rate in phase 3. So not as good as the 52%, which is sort of expected. But now my time per trajectory has like been divided by almost 2. So it's only 2.6 seconds to get a new independent samples, which means that I should expect my phase 3 to last only 3.6 hours. So I've almost cut the phase 3 duration by a factor 2 with the neural network. And I'll leave you with my conclusion. I'm not a deep learning expert at all, so any insight or help that could improve my settings would be appreciated. Thank you for your attention.
Sorry, it's not an insight. I was wondering, how did you choose the architecture of the DNN? How much did you try? Did you have any insights?
So that's why I'm asking, yeah, for insight, because basically I'm really new to the deep learning field, so I tried different things. Firstly, it was not working. I had 2 layers, didn't know how many layers, how many nodes. So then what I did is, because my gravitational problem is always complicated, it was hard to know whether it was not working because of the data, because of my architecture. So I basically produced fiducial, very simple distributions, derived their gradients, and then because the gradient of a Gaussian of the log of the Gaussian is linear function, then I knew that my neural network should fit this. Then I complicated my fiducial distributions, adapted sort of iteratively my network, and in the end, I don't know why it's working. This 3 layers, 10 times the dimension, then 100 times, then 10 times. Actually, it's working for dimension 10. Maybe it's not working for dimension 17. Maybe it could be optimized. It's working for the moment, so I'm fine with it, but I can't really know.
So I'm not sure that the acceptance rate is the right metric for success here, because I can always I can always choose a really small step size and make the acceptance rate.
You're completely true. The right, I believe, metric is the time it takes for me to acquire a new statistically independent sample. That's proportional to 1 over the acceptance rate, basically.
Okay, but I guess the time to get to a certain level of convergence might be the best metric, I would guess.
Yeah, that's I believe what I call the time per statistically independent sample.
Possibly related, yeah. Okay.
So why wouldn't that be related?
Well, it probably is closely. Yeah.
Well, so for me, the decision was to finish the run after 5,000 statistically independent sample. I think there's no official threshold there. In the community, that's basically the number that we've picked, or 10,000 at most. But so basically, if I just multiply 2.6 seconds by 5,000, I get the time it takes for the phase 3.
Thank you.
Any other question for Mark? All right, I think we can thank him again.